Yeah, it's helpful. Let it be known. All right, so we're going to pick up with heaps. This will be our last class dealing with heaps. The first one we did kind of an overview of how they work, how you add to a heap, how you remove from a heap, how you implement a heap using an array. Second class, we started coding it. Okay, I think we got through our add method, so we can add stuff to a heap. What we're going to get into now is the remove method. So we're going to look at how we remove from a heap, and we will conclude with that before moving on to other stuff. Okay? So if we take a look, just a quick review of our code. Here's our heap class. We're going to instantiate this once. This class contains all of the functionality for adding and removing from our heap. We have a get size and that sort of thing as well. We have an ice cream class. This is what we're putting in our heap, ice cream objects. And the value that we are using to order our heap is the temperature of the ice cream. We randomize the temperature from, looks like 0 to 50 degrees, or 0 to 49, and then we sort them in the heap based off of that, or order them that way. Okay? And then finally, we have a driver. Very simple. We create our heap at the top. We loop through 10 times and add 10 different ice cream objects to our heap. Okay? Everybody good with this? So what we're going to do now is look at removing. Because this is really the only other thing that we need to do with our heap. You don't typically search a heap. Now you can. If you search a heap, it's an indexed structure. It's going to give you ON performance. Not very good. You can do it. But if you are searching a data structure, you're better off using a different data structure. One we haven't learned yet, but we'll get to that soon. Okay? So, adding, does anybody remember what the cost to add to a heap is? Log. Oh, log n. Good. Log base 2 of n. Same thing for removing. Searching is ON, although you shouldn't do it. All right, so let's pick up here and do some coding. I'm just going to do kind of the same thing we did here. I'm going to copy our loop. And then instead of saying heap.add, I'm going to say heap.remove. This will return our ice cream object, and I'm just going to print out the object. Okay? Heap.remove.toSTRI. Good? So now that we've got our remove method called, we need to actually code the remove method. We did a really good job of commenting our add method. Well, let's do the same thing for remove. So we'll say public ice cream, because we're going to be returning an ice cream object, remove. And we don't need to pass any parameters to it, because a heap always removes what element? Welcome to our illustrious TA. Thanks. You're welcome. The top element, good. So you always remove the root element in a heap, and that's what we're going to be doing here. Okay, so let's take a look at the logic for this. Now, before we get into coding, let's review the actual algorithm for removing this. All right, so let's say we got a heap. It looks like this. And let's make up some numbers. Some max heaps, so we'll say like 85, 30, 47, 21, 8, 13, 42, 11, and 9. When we remove, the first thing we do is we take this guy and we remove it. Okay, that's our root. We need to get rid of it. So once that's gone, basically what we're going to do is we're going to create a temporary reference to it and put it over there. And we need that so that we can return it at the end. Okay, we did this with our previous data structure. We're going to do that for this one as well. The next thing that we do is we need to take the element that's in the last position and move it up to the top. Okay? The reason we do that one is because once we move it to the top, that is the only element that we can move and still satisfy the first rule of heaps with it being complete and balanced. If we move any other node, we're going to have a hole in the tree, and that's no good. Okay, so we're going to move this guy up to the top. Good so far? Okay. Now that our structure is fine, the next thing we need to do is fix the ordering. So the way we do that is we take the node that we moved up to the top and we compare it to its children. It's a max heap. So we look to see if either of the child values are larger. If they are, then we swap. Well, in this case, both of them are larger. 30 and 47 are both larger than 19. So we're going to swap with the larger of the two. So this becomes 47, this becomes 19. And then we do it again. Okay, now that it has new children, we look. In this case, only 42 is larger. So we're going to swap here. We'll put 42 here, we'll put 19 here. And we're done. Good? Questions? All right, let's code it. So, first thing we're going to do is let's store temporary reference to root object so we can return it at the end. Ice cream temp equals. We'll say temporary, not to be confused with the temperature. Okay. So we know that it's all stored inside of an array called heap. At what index is our root? Right, it's at index 1. What's stored at index 0? Nothing. Good. Nothing is ever stored at index 0. All right? Remember, in order for our math to work out with multiplying by 2, dividing by 2 to access the parent and child values, our root has to start at 1. Otherwise, it messes up. Okay? So now that we've got that, we've got our root stored. At the very end, we're going to return the original root. Now that we've got that taken care of, now we need to do everything else in the middle. So let's come up here. Remember step 2? What did we do after we kicked off the root? Right. Move object in the last position to the root. Heap at position 1 equals. How do we get access to the object that's last on the list? Size, good. So if you remember, when we did this, when we were adding, we knew to add it at position size. Okay, so if we have a situation like this, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is at index 9. What is the size of this heap? Not what is the size of the array, what is the size of the heap? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can get access to the node, the object that's at the last position, by saying heap at position size. Right? At the very end, we're going to say size minus minus. We're going to reduce the size. Now, what if the heap's already empty? What's this going to do? Are we going to crash?
Yes.
Yeah. Bless you. Make sense? the last thing that we should do is this. Okay, so when we take, we drew that picture, blah, blah, blah. When we take this object, we already did this, okay? We store that in a temporary location. And then what we do with this line of code right here, we say heap at position 1 equals heap at position size. So that just copies this. If this value is, 19 here, then all that does is that copies it up here. Okay? We copy it. We take position 1 and we assign it to whatever's in position size. But we also need to delete this. Now in Java, we don't really have the ability to delete memory locations like we do in other languages. So what we want to do is, we want to make sure that that element of the heap no longer references an object. Okay? The only way we delete things in Java is by removing references to it and waiting for garbage collection to come and clean it up. Okay? Whenever that is. Okay, you can request it, but it can tell you no if it doesn't want to. So yeah, that's exactly what we're doing. We're going to say heap at position size equals nothing. Good? All right, so now we've got our object moved up to the top of the heap. What is the next step? What do we do here? Very good. Now we are going to repeatedly compare it to the children to determine if a swap is necessary. Now, do you remember what kind of control structure we used in adding? You guys know what control structures are? Control structures are a fancy word for the different type of statements in terms of controlling where the code goes, controlling the flow of code. So a selection statement, an if statement, is a type of control statement. A loop is a type of control statement. Does that make sense? Just controls how the code flows. So what type of control statement did we use in the add method? What? Very good. It's a while loop. Okay? Are we going to use the same one here? Yes. Okay, good. So let's come up and look at this. So if we look for the add method, we continue to loop as long as index was greater than 1. But in practical terms, what this means is we're going to continue to loop as long as there are parents to look at. As long as the index where we are has parents. Because what we're doing here, and this is our add method, is we're determining if a swap should be made with the parent. We're doing the opposite down in the remove method. We're determining if a swap should be made with the children. So what do we want to put here? Roughly, in terms of English words, not in terms of code. What do we want to put there? Yes?
Index is less than size.
When are you trying to get it to stop?
When it's not large, when it's larger than both the children, or when it's the last thing in the heap, right?
Yes and no. So look at this. So let's review this, because we're doing the same thing here. Do you guys remember that I told you there are two conditions under which we stop looping when we're adding? The first condition is when the index no longer has parents. The second condition is when the value of the parent is not smaller. So when a swap doesn't need to be made. So we stop if there are no parents, and we stop if a swap doesn't need to be made. Okay? Now, which of those two conditions is handled here? No parents. Very good. The no swap needing to be made is handled here. If this if statement is false, then we break out. Nope, the parent value is larger, no swap is needed, stop. Okay? We have the same situation when we're removing. We want to stop looping, stop checking for a swap under two conditions. The first is if there are no children. If there are no child values, then there's nothing for us to swap with. We need to stop. The other condition under which we should stop is if both of the child values are less than or equal to the parent value, meaning no swap is necessary. So we could take the same logic here, use the terminating condition of the while loop as the basis for checking whether or not there are children, and then inside of that, check to see if a swap needs to be made, and either continue swapping or break out if the child values are less than or equal to them. Okay. Good so far? So continue to compare root to children as long as there are children. What should we call it? Parent. Okay. So, in order to get this, we need to store the index of the node let's say object. Node is just the same word for object. Of the object we moved to the root. Int index equals 1. So we'll say while index something something. How can we determine if we have this structure set up? I'm going to write the index to all of these in them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have size equals 10. And I wrote the index to these objects inside of them. This isn't the value. It's not their temperature. This is their index. Okay? So what we want is, remember, the while loop condition that we're setting up now is responsible for determining whether there are any children at index. We want to enter the loop. We want it to be true if there are children, and we want it to be false if there are no children. Yes?
You can check if an object exists at index times 2.
Okay, we could certainly do that. Look at this for a second, okay? But before we get to that, look at this. What do you notice about where children stop occurring? Does 4 have children? Yes. Does 5 have children? Yes. Does 6 have children? No. At what index do we no longer have children? What size? 10. So at what index do we no longer have children? 6. Agreed? Okay. So what is the last index that has children?
5.
What's size divided by 2? 11 divided by 2 is still 5. Size divided by 2?
6.
6. 6. 7. 7. Size divided by 2 gives the index to the last object with children. Always. Yes,
So that's why it's a log 2?
that's why it's so.
Is that why it's a log 2?
Yes, yes. Makes sense? So, based off of this information, what do we write there? We want to continue looping. We want to enter this if index has at least one child. Think about it a second. So, what if we said in this configuration, before we went and added all this, when size was 10, if index equals 5, size divided by 2 is 5. We're going to do less than or equal to. Right? Because if we get to index 6, 6 less than or equal to size divided by 2 is 5, that's false. Right? So this is what we want right here. Index less than or equal to size divided by 2. Good so far? Yes?
Quick question, how would you go back, like, what if, like, the very bottom number was a large number? How would you continue to move that up the chain?
Well, are you talking about adding or removing?
When you're comparing?
So what we're going to do is, you have to keep in mind that when we move that object to the top, the rest of the heap is ordered properly. So the highest number wouldn't be at the bottom. It'd be impossible for it to be at the bottom. Okay, the highest number would have to be one of the two children of the root. Okay, and that's what you have to kind of keep in mind. If the highest number couldn't be at the bottom because that object's parent would be lower, in which case the ordering wouldn't be right. Okay, so that's what you have to kind of keep in mind. Okay, so we're going to continue to compare the parent, which is the index, or continue to compare index to its children as long as there are children. Okay? So once we come inside, what we want to do is, now we have determined, if we enter this loop, we've determined that it has at least one child. Maybe not two, but there's at least one, right? So we want to go ahead and get the index and get the values at those two positions. Okay? So, we're going to say store index and values of children. So we'll say int left child index equals, how do we get the left child index?
Index
times 2.
Good, index times 2. Int right child index equals, or left child index plus 1. Efficiency. Does that make sense? Same thing. Now, can we determine with 100% certainty that there is a left child?
Yes. Yes, because we've just checked that their children exist.
Yes. We know that there is at least one child. Because we know that there's at least one child, as determined by this condition, and we know that there are no holes in the heaps, it would be impossible for there to be a right child and not a left child. And because we know there's at least one child, logic tells us that that child has to be the left child. Now there might also be a right child, but we know with 100% certainty that there is a left child. So we will say int left child value equals heap at position left child index dot get 10. Get 10. Now here's the thing. Do we know for certain that there's a right child? Can we determine if there's a right child?
Yes.
How could we do that?
With size.
Can do it with size? Certainly. How do we do it with size?
You could check if the check if left child index equals size, or right child index, sorry.
If right child index is less than or equal to the size, what's that tell you?
There's a right child.
There is a right child. Okay. Again, drawing these out when they're difficult to visualize is helpful. One, two, three, 4, 5, 6, 7, 8, 9. Size equals 9. So when we are here at index 4, we say 4 times 2 equals 8. That's what we did right here. That gets us the left child. Say 4, and then left child plus 1 gets us the right child. The index of the right child, which is 9, as long as it is less than or equal to the size, we know it exists. Okay, now there might be additional ones here which make this go up. But here's the question. So if there's a right child, awesome. What if there's not a right child? What do we do with this? So we can do a couple things. And it's important to keep in mind where we're going with this. Ultimately, what we want to determine in storing these values, we want to determine which of the two child values is larger. Okay? And the larger value then gets compared with the index, or the parent, to determine if a swap is necessary. If there is no right child value, then we don't want to even consider that for the swap. Right? We'll immediately say the left child value is larger because the right child value doesn't exist. We can do it that way, or we could initially give the right child value a ridiculously low value. One that we know would never cause a swap to occur. Does that make sense? Either way is fine. Okay? Typically, I just give it a really low value, but probably not the cleanest solution. Okay? You could say, I think it's integer.min value. Like the lowest possible value for integers. And then if there is actually a right child, then we'll actually give it this value. Then we'll move on. We'll say determine the larger of the two children. Int larger value. Int larger effect. If right child value is larger than left child value, then the larger value equals the right child value, and the larger index equals the right child. And there's 100 different ways to do this. Okay? This is just a quick one. I'm breaking this out a lot more than I normally would. I wouldn't typically declare as many variables like this, but for the sake of understanding it the first time you go through it, it's easier when there are more variables and it's broken down, as opposed to having larger code statements. So that's why. It looks like a lot more code than it really is, but just keep that in mind. All right, so the next thing that we want to do, now that we have determined the larger of the two children, determine if a swap should be made with the parent and the larger child. If heap at position index dot get temp. So this is the temperature of the object that we move to the root. If this is less than the larger value, we swap, right? Right? The parent value is less than the larger value, then we swap. So we'll swap, and we'll say heap at position index equals heap at position larger index. Good? Let me comment this loop, so we'll swap, and then we're going to update the index since we moved it to a child position. Index equals larger index. The larger index stored the index of the child that was the larger of the two. So we effectively swapped it with the parent. Then we need to update index to reflect the fact that we swapped it and it's no longer at that position. Now, else meaning what? If we hit the else statement, what's that mean? Say it loud.
Else return something.
Return what?
A statement saying that there is no swap to be made or something like that.
So what happens if we have a situation where there are children, but we don't need to swap? Is that good? Yeah, it means we're done. Okay, so what we want to do there is the same thing that we want to do up here. Like I said, we want to be done. So we're going to say the parent value is larger, no swap is needed, break out. When we break out, we're going to update the size, and we're going to return the original. So let's see if this works. We might have some errors. Let's compile here. What I'm going to do is let's actually only remove 5 of these. And then let's add a few more. So let's add 10, remove 5, and then add 5 more. Just as a deal. All right, so I'm going to let it go quick. So we'll add 1, add 2, 3, go faster, 4, 5, 6, 12, 7, that's some cold ice cream, 8, 9, 10. Great. All right. So let's see if we did this right. So now we have a heap. We didn't have to make a lot of swaps, so good. So what we want to do is now we're getting to the point where we're going to remove them. So let's walk through this and make sure that it's doing what it's supposed to be doing. So we're in our remove method. The first thing we do is check to see, is the size 0? Is it empty? It's not, so we come down here. we're going to store a temporary reference to the root object, which should be 47. So we do that. Now we're going to say heap at position 1 equals heap at position size. Well, size is 10. So we should be pulling, hopefully, this object and putting it up at 47. So let's see if that's what happens. Okay, good so far. We move that object to the top. The last thing that we're going to do is we're going to set this equal to null. And we do. Now, this will disappear once we update the size. Okay, it's just the way it's displayed. But this is now gone. Okay, so step 1's good. We effectively removed the left object up to the root. We're going to keep track of the index, which should be 1. Okay, this was for when we had it. So now we want to keep looping while index is less than or equal to size divided by 2. So I'm going to grab index. Index is 1. So 1 is less than or equal to 10 divided by 2. So we are going to enter the loop. And then we're going to grab the index to the left child and the right child. What should those be? What's the index to the left child? 2. What's the index to the right child? 3. Do we understand that? This is index 1. This is index 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay? So the left child we get by multiplying 1 times 2, and the right child we get by multiplying by 2 and adding 1. All right. So once we have that, then we're actually going to grab the values at those positions. Okay, so we'll grab the left child value, which is 39. We'll grab the right child value, which at this point in time we haven't determined whether or not the right child actually exists. So we're going to give it a value that would never cause the swap to occur, which is integer.min value. Now again, this isn't necessarily the best way to do it, but it's the fastest. Okay? Then we want to make sure that the right child actually exists. In this situation, it does exist because the right child index is less than or equal to the size. So we're going to set the right child value to its actual value of 44. Okay? So we come down here, we declare 2 variables that's going to hold the larger of the 2, and we check to see is the right child value larger than the left child value. Is it? That would be a good test question. Is 44 larger than 39? True or false? Fill in the blank. True. That was a hard one. All right, so that's true. So we enter the if statement, and what we're doing here is we're setting the larger value and the larger index to be the right child. Now, once we've determined that the right child is larger, what we want to do is check to see if the larger value is larger than the parent. Is it? Is 44 larger than 21?
No.
Thanks for that. Yes. Are you guys awake? Spring break does bad things. Yes. So we swap them. So 44 is going to go up to the root. 21 is going to go down to the right child. And then we're going to update index. We're going to update index to be the right child, which is 3. Now we're going to repeat the process. So we get the left and the right child. We determine that the right child exists of 0. Compare the two. We figure out that the left child is larger, so we hit the else statement. And then we compare the left child with the parent and determine that a swap is or is not necessary. No, right. It's not necessary. So we hit the else statement. We update size. which removes that, and then we finish. So, did we effectively remove the object? Is our heap structured and ordered properly? Sure is. So I'm going to let it play. Let's do the next 5. 44 gets removed, 15 gets shifted down left, then it's going to get shifted down right, and then, hey, there are no more children, so we stop. Gets removed, shifted left, shifted right, excuse me, shifted left again. All right. 21 goes, or 0 goes left, 0 goes left again, and we're done. And then we go back to adding. We're removing one more. We can do this for a while. Question?
Thank you.
You're welcome. So what questions do you guys have on this? Yes?
How does JGraphs data structured as a heap? You could have just made any data structure and called it a heap, right?
Probably. I honestly don't know how they determine what it is. I don't know if it's a naming thing or if they look at like what you're putting in. If there's a way that they're analyzing the code to determine if it's a heap. I don't really know. Yes?
The heap gets its position, like say you remove an object, put it at the top, it knows to continue going from the while loop statement where it's that index is for that sole position that we're at.
Yeah, if you look, we set that index
To the one that's at the top.
to 1 right here. Okay. So when we remove, we set it right here. And notice we do that right before we hit the while loop. Because we're always going to move it up to the root, and that's always going to be position 1. So we just say that's where the index is. And then at any point in time, well, there's only one point, that we perform a swap, we update the index to be the index of the child that we swapped it with.
So you're saying that before the while loop, we take out the top one already?
Right.
We do that?
Correct. Yes. Yeah, we store the top one in this temporary variable here. That's like the first thing that we do. Once we make sure that there's something to remove, we store heap at position 1 in temporary, and then at the very end, we return it. Other questions on this, guys? Okay. I'm going to put this on Canvas. You are welcome to use this as a starting point for your programming assignment on priority queues. Obviously, you're going to have to make some modifications to get it to work with what you need it to do. But anything I post on Canvas, you're welcome to use in your projects. Yes, sir?
You said that there are different ways to do this much more cleanly because you're adding more variables for the sake of teaching. I guess we just have to figure that out when it comes to modifying for the program and all that.
Yeah, if you just look at, this, you can see that there's a lot of like local variables declared. It just kind of bloats it. It's not necessarily wrong, but it makes it longer than it needs to be. There's also other ways to handle not knowing if there's a right child or not. There are cleaner ways in terms of this. You could run into issues if you ever change from a min heap to a max heap. Like, you just have to make sure to change that to a high value. It's not a very elegant way to solve the problem. It's kind of a ghetto fix, but it works. And the only other thing you have to keep in mind is that in your program, remember, you never, when you are adding, you never swap with the root. Okay, so there's different ways you can handle that, whether you handle it in the heap itself, or whether you handle that in the driver in terms of not swapping. That's up to you guys. Okay, question?
You know how you did int like child value equal integer? Why can't we do it? Why can't we set it to null?
Because you can't have null as a value for int.
Okay, yeah, that's true.
That's all. If we were storing, and that's another way to do this, instead of storing the actual value in the index, if we stored references to the objects at the index, then you can just let it equal to null. That would be
Thanks.
good question. Yep. Other questions? All right, very good.